In the previous video, we learned about radicals, so now we are going to learn about simplifying and combining radicals. So let's start with this example. We are going to simplify square root of 4 times 25 and separately square root of 4 times square root 25. So let's take a look. Square root 4 times 25 on the left is square root of 100 when we multiply what's in the radicand. Remember that term, radicand, means what's inside the radical. And then square root of 100 is 10, because this is asking you what times itself is 100. The answer is 10. And then over here, we have square root of 4 is 2, because what squared makes 4? That answer is 2. And what squared makes 25 is 5. And then 2 times 5 is 10. So here's why I'm showing you both. They are equal. At the beginning, they are actually equal, and it's because at the end they are equal. So let's simplify another one. Cubed root of 8 times 27, and separately, cubed root of 8 times cubed root 27. So on the left, if we multiply the inside first, the radicand, we get cubed root of 216. So this is asking what number times itself 3 times equals 216. That number is 6. If you want to check, you can put 6 cubed in the calculator and you will get 216. Separately, over here, what number times itself 3 times is 8. That number is 2. And then cubed root of 27, what number times itself 3 times is 27. That number is 3. And then 2 times 3 is 6. So these are equal. Therefore, our starting point was equal. And this is not a coincidence. So we're able to now multiply radicals by merging the radicands or by factoring and breaking apart the radicals to evaluate smaller radicals. And so in general, this is going to be a nice rule for us to use. Okay, you can go back and forth with this rule. So if you start with the left side, you have 2 separate nth roots, like 2 separate square roots, 2 separate cubed roots, and you're multiplying. You can combine them like this on the right side, or if you're starting with the right side, you have an nth root, square root, cubed root, or so on, and you're multiplying the radicand, you can separate it. Now, let's look at an example where we are dividing. So, simplify the square root of 81 divided by 9, and then separately, square root of 81 divided by square root of 9. So, on the square root of 81 over 9, 81 over 9 is just 9. And then what number squared makes 9? Well, that answer is 3. Over here, what's the square root of 81? What's the square root of 9? Well, square root of 81 is 9. Square root of 9 is 3. 9 divided by 3 is 3. So these are equal as well. Therefore, what we started with was equal. So we can divide the same way with radicals. We can split them up. So the nth root of a divided by b can be separated as the nth root of a over the nth root of b. And if we start with them separated, we can combine them like the left side of the equal sign. So let's simplify. We have 2 separate square roots, but we are dividing them. So we have square root of 50ab squared on top, divided by square root of 2a on bottom. 2 times 25, which makes 50. And then we just put our multiplication symbols to clearly see the factors. And so notice just a rearrangement here, because we just talked about this. We can separate into separate square roots if this radical, if we have multiplication of our factors. So notice we take the 25 and the b squared, and we're going to put it in its own square root. And then everything else, the 2 and the a, are going to go in a separate square root. And we can write those as being multiplied. And it's the same as what we have up here, just it looks different. Now, why we picked the 25 and the b squared, you might see maybe a reason why we picked those. Those are both perfect squares, and the 2a on bottom is in the square root divides out with the 2a on top. So those divide out, and we get 5b as the answer, because square root of 25, b to the second power, is 5b. Now, that's one way to have done this, to simplify this expression. Here's another way. Combining it initially. So initially, instead of 2 separate square roots getting divided, we could just make it one big square root with division in the radicand. and then simplify inside. We have a 50 divided by 2. We have an a on top divided by an a on bottom. And so we get to simplify. And we end up with a 25b squared inside our square root, which gets us our same answer, 5b. So to simplify radicals, we can use either of those two techniques. And so let's try this. We are going to simplify square root 300. So here's step 1. Find perfect square factors of the radicand. So find perfect squares that go into 300 as far as multiplying. So think about one of these options. 300 is the same as 100 times 3. And this is a good choice because 100 is a perfect square. It is 10 squared. So then we can separate this and say that square root 300 is the same as square root of 100 times square root of 3. And then we know square root of 100 is 10. And we don't know square root 3. It's not a perfect square. It's actually an irrational number. So we leave it as square root 3. And so there's an invisible multiplication symbol still right in between here. So this is really 10 times square root 3. And that would be the final answer. The other option is maybe you didn't recognize that 100 was the biggest perfect square inside of 300. And maybe you initially thought, oh, 25 goes into 300. So 25 times 12. Well, this also works. 25 is a perfect square already. And then if you break down 12, 4 is a perfect square. So then 25 and 4, we know the square roots. And so square root of 25 is 5, times square root of 4, which is 2, times the square root of 3, which we leave. And that's the same answer. So you could get this answer by breaking down 300 different ways. The easiest way, and just so you're aware in the future, is to look for the biggest perfect square that goes into your radicand. So notice it was less steps when we broke 300 down into 100 times 3 than it was for when we broke 300 down into 25 times 12. So then, part 2 here, step 2. Determine the prime factorization of the radicand and factor out pairs of the same factor. This is for square roots. We are specifically talking about square roots, so we are looking for 2 of things, okay, pairs. And so in this case, here's another breakdown for 300. So I'm just showing you different options here because it just depends on what you would have naturally came up with. So maybe you said 300 is 2 times 150. Okay, so 2 is all by itself. It's just a prime number. Let's break down 150. So I can say that 150 is 10 times 15. Okay. And then 10 is 2 times 5. 15 is 5 times 3. Now, because we are talking about a square root, this is a square root and the index is an invisible 2, we are looking for pairs. So we are looking for 2 of things. So here's 2 2s and here's 2 5s. And so we're going to pull out one of each pair. And so we end up with 2 on the outside, 5 on the outside, and 3 stays in the inside, which is the same answer. And so the reason why we pull out one of each pair is because we technically take the square root. When it says pull out one of each pair, you're officially taking the square root at that moment. So square root of 2 squared is 2. Square root of 5 squared is 5. That's why we only keep one of them on the outside. Okay, how about this? This one I want to make sure you're aware of because the rules we just talked about as far as separating and combining radicals, they don't work here, and you're going to see why. So let's try an example. Square root of 9 plus 16, separately, square root of 9 plus square root of 16. So square root of 9 plus 16, in the radicand, you're going to combine because the radicand's holding together the 9 plus the 16. So you would say this is square root 25, which we know is 5. Over here, square root of 9 is 3, square root of 16 is 4. And so when we add those, we get 7, which these are not equal. Therefore, the original were not equal. And so this is something to be very careful with. Don't think that this rule works just because it did for multiplication. So the difference was there is a plus sign this time. So plus and minus in the radicand You cannot separate them. The rules we just went over, those previous examples, they had multiplication signs and division signs. So those same ideas of splitting up or combining the radicals don't work when you're adding and subtracting. Okay, so in general, if you have two nth roots, so like two square roots or cubed roots, and you're adding, you cannot combine them into one nth root. Same thing happens with subtraction. So now, let's talk about when we can combine radicals. So when we combine like terms, we add or subtract the coefficients. So let's look at a simple example and then generalize this to radicals. Okay, so simplify both of these expressions. 3a plus 2a, separately 3a plus 2b. So in the first expression, that's a total of 5a. You had 3 of something plus 2 of something, so there's 5 of that something. The next expression, there's nothing to combine. They're different items. You can't say I have 5 of any one thing. It's 3 a's and 2 b's. So adding radicals is very much the same. So like radicals, they have the same radicand and the same index. Okay, the coefficients are the only thing that's different here. So, for example, if we simplify 3 square root 7 plus 2 square root 7, and we try to do 3 square root 7 plus 2 square root of 5, we're only going to be able to combine the ones with the like radicals. And so the next one, there's nothing to combine. Okay, this is a total of 5 square roots of 7. Over here, they're different radicals, cannot combine them. This is as simplified as this is going to get. Okay, take a look at this. Let's simplify this expression. I know it looks kind of crazy, but we're going to work through it. So we have lots going on. The first thing to notice is that these are all square roots. So that's a good thing that we're only working with the one index. It's a 2, so square roots. So we're going to start breaking apart these radicals. So in the first one, I'm going to take 162 and I break it down, and there's lots of ways to factor it, but if we notice that it's 81 times 2, this is going to turn out pretty good for us because we know the square root of 81. Okay, the next radicand, 32, let's say I didn't recognize that 32 had a 16 in it. That would have been the best choice, but let's just say I thought 32 should be broken down as 4 times 8. Okay, we'll still work this out. Notice also that x to the 5th, I'm separating it as x to the 4th times another x. And there's a reason for that. I am going to take the square root of all of these factors that I can, and something to the 4th is actually something squared. Okay. The next one, 200, I'm going to break down as 2 times 100. 100 happens to be a perfect square. It's the biggest perfect square inside of 200. And then the last one, I'm going to break 72 down as 9 times 8. And then x cubed, I'm going to break it apart as x squared times another x, because this is a total of 3 x's, x cubed. Now again, there's possibly a better way to break down 72, but let's say I didn't recognize what perfect square was in here. That's the largest perfect square that makes 72. So I just break it down any way I know how, and I know that 9 times 8 is 72. Okay, so that's our first step. Let's keep going. So nothing yet to simplify in the first radical, the first term. The second radical, I know that 4 is a perfect square, but then if I break apart 8, 8 also has another perfect square. So 8 is 4 times 2. Okay, so I just broke down 8 because it also has a perfect square in it. Okay, the next radical, I already had factored out the biggest perfect square that I could from 200. And then the last one, let's see if you see it before I write it. Are there perfect squares still in here that I can factor out? Yes. So 9 is a perfect square, but then 8, I can break that down again as 4 times 2 because 4 is a perfect square. Okay, now I start taking square roots of factors that I know. So everything's getting multiplied. So this is actually critical that you recognize that you're multiplying. If you were adding, we could not do this. But because it's times signs everywhere, you can go ahead and break this down. So square root of 81 is 9. So that came out of the radical when you took the square root. And then square root of 2 and square root of x, we don't know those. They're not perfect squares, so they're going to stay inside the square root. Then square root of 4 is 2. Square root of 4 again is 2. And then right here, square root of x to the 4th is x squared. Because if you think about it, remember if you have an exponent raised to another power, you multiply. So this is really, initially you could say that this is x squared quantity squared. So when you take the square root, you just get x squared. And then the 2 and the x stay inside because they're not perfect squares. Then over here, square root of 100, we know is 10. So that 10 is going to come out. And then back here, we know square root of 9, square root of 4, and square root of x squared. So square root of 9 is 3, square root of 4 is 2, and then square root of x squared, it undoes the exponent here because you are taking the square root of something squared, and you just get x. Now, technically, we should put absolute value bars here, but for the sake of this problem, we're just going to leave it as just x. And then notice, after we simplify a little bit, we have all of the same radicals. Okay, so all of the radicals, what's remaining inside a square root is the same. It's all square roots of 2x. So we can combine because these are all the same radicals. So we have 9x squared minus 4x squared minus 10x squared plus 6x squared times square root 2x. And then we can just simplify that, and we get x squared square root 2x. Okay, so I know that was quite a bit to look at, but just so you're aware, if you don't know what the biggest perfect square inside of a number is when you start to factor it, just pick any factoring you know and then break it down as you go, like we did in a couple of these radicals. And then as far as the variables go, like x to the 5th, you want to think about even numbers if you're talking about square roots. So you would break apart something with an odd power, like x to the 5th, as the even power, and then whatever's left over. So x to the 4th, and then the leftover x to get back to 5, because you can take a square root of something like this, x to the 4th. And in the next video, we will talk about combining radicals even more and operations on them.